Hello, welcome to chemistry lesson 5.07 over metallic and hydrogen bonding. So we're going to kind of quickly talk about the two last forms of bonding that we want to discuss. And the first one is metallic. And we had said previously that metallic bonding, and this is going to be mostly we're going to be talking about the intertransition metals for the most part. So what do the intertransition metals have and we're talking about, these are also, remember, non-main group. Non-main group. What do they have that the main group don't? I'm going to hit focus here real fast. Make sure this is all the way focused. That's better. Well, it's represented, and I'm going to use a highlighter to highlight what I'm talking about. It's represented, you want to think more blue. These black fuzzy clouds around the positive circles represent what the intertransition metals have that the main group elements don't. And maybe you already guessed it. It is d orbitals. So all of the blue are representing d orbitals. So if this is copper, we've got d orbitals, and those are actually the valence electrons. So the valence electrons for these guys reside, they hold the valence electrons for the intertransition metals. Then when your valence electrons are in d orbitals, something really unique can happen. So again, the positive or nucleus, so let's just put that down. Positive represents the nucleus. So if I'm an electron, well, let's say first, so these d orbitals hold the valence electrons and they overlap. They kind of overlap each other. It's a little bit difficult to see, but let me get a pointer. So we have overlap right here, 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 right here. Everywhere they touch, they overlap. So if I'm an electron and I have something that generates a force, I can start here. So if I'm an electron, and this is what happens when we hook something up. So we talked about the fact that gee whiz, I need my whiteout. We talked about the fact that metal things that have metallic bonds are good conductors of electricity, and this is why. All right, so I have an electron here, and I'm going to give it a push or a force. That electron can follow any path it wants to go through each of these. Let's say this is copper. So this is a copper nucleus, copper nucleus, copper nucleus, copper nucleus, copper nucleus, and this would represent a sheet of copper. Each of the positive signs represents a single atom of copper, and then the blue around represent the d orbital valence electrons. So when we put current to copper wire, we're basically sending electrons to the end. And what happens actually is this electron bumps this electron, bumps this electron, bumps this electron. I can go the other direction. So if I do an electric force this way, the electrons can flow this way because the d orbitals overlap, and everywhere they overlap is where the electrons can flow. We call this property sea of electrons. Kind of like how water can go wherever it wants to within a structure. It flows. The electrons flow like water flows in the sea because they're not tied to a single nucleus. One of the examples we have is back in the 60s, a big thing to do in California was to have a commune. And what you would do is you would sell all your stuff, and then everything that was at the commune was owned by everybody. Nobody had any, there were no possessions, which I think would be a little awkward. I'm not wanting to share, toothbrush or underwear, but intertransition metals very much are that way. This electron doesn't belong to this nucleus. it could have flowed over to this nucleus at any point in time. And so the d orbital overlap also help provide the bonds. And so we get a very different dynamic in these intertransition metals. They don't care about octets, kind of like hippies in a commune don't care about owning a Bentley. They don't mind if all their electrons head this way and these electrons head that way. Now that's a little oversimplified, but that's kind of the gist of metallic bonding. All right, hydrogen bonding. Remember, I've got some diagrams here. I've got water molecules. This is oxygen. My black marker's dead. I need a different black marker. This is oxygen. So for all of these, this is oxygen, this is hydrogen, and this is hydrogen. It's kind of hard to see. First of all, there's a covalent bond. So we're talking about molecules that are covalently bonded together. So when we talk about hydrogen bonding, this is bonding between molecules. Remember, molecules already have covalent bonds. So for that reason, we call this intermolecular. And there's a bond between hydrogen and oxygen here, and there's a bond between hydrogen and oxygen there. So I have two covalent bonds. But sometimes in a covalent bond, atoms do not share electrons evenly. So we have in covalent bonds, they're subject to something called electronegativity. Or in a sense, you could call it uneven electron sharing. Hydrogen's trying to get rid of electrons, and so they both have this oxygen, even though it's sharing electrons, it's got a satisfied octet, because sharing satisfies an octet just as well as giving or taking. So this guy is sharing pretty well, but these guys really didn't want an electron all that bad. Hydrogen likes to go to the +1 state, but oxygen was only 2 away, so it really wanted to gain electrons. So you have a tendency to gain here. And you have a tendency to lose here, giving this a high electronegativity, and this has a low electronegativity. So because of that, so we start off, and I'm going to kind of do a list, and I may have to write down on my page a little bit more. I'm going to switch colors here. So let's talk about where this hydrogen bond comes from. Source of a hydrogen bond. And remember, it only happens, the only elements that have electronegativity high enough to make this happen are nitrogen, oxygen, fluorine with hydrogen. So these are the only three that have an electronegativity that's high enough to create a hydrogen bond. I'm just going to go ahead and slide down. All right, so we start off, and let's just talk about the source of hydrogen bonding in water. Oxygen has a higher electronegativity. And I'm going to abbreviate electronegativity as eneg for the reasons we just explained. Because hydrogen has a tendency, a higher electronegativity, the shared electrons are pulled closer to oxygen than to hydrogen. And I better just write O because it's not diatomic there. I don't want to confuse you. Because the electrons hang out around oxygen more, what charge do electrons have? Well, yeah, negative. So having the electrons closer to its nucleus Have you ever hung out with somebody who was really negative and they were always kind of talking about how awful everything is? And after a while, you kind of felt like you were getting down too. That's kind of what happens to oxygen. Because those electrons are closer to the oxygen nucleus, the oxygen starts to kind of pick up part of a negative charge. It's not a full negative charge because this isn't an ion where we're giving and taking, but it has a partial negative charge. Gives it a partial negative charge. And by the way, the symbol for that is like a weird, looks like almost like a bent quarter note. That means partial positive. I'm sorry, negative. And as a result, the hydrogen have a partial positive. And you can see that on this diagram here, negative, positive, positive, negative, positive, positive, negative, positive, positive, not a full one, but a partial. So what happens, we already talked about what happens if we put a positive charge and a negative charge close to each other. Well, opposite charges attract. And that's represented by this dashed line. So you can see in this diagram, there's dashes between the partial positive hydrogen and the partial negative oxygen. And you have dashes here. You've got dashes here. That attraction is a bond. And we call that a hydrogen bond. This has applications in any science class you take, whether you're talking about chemistry, biology, biochem, marine science, and especially we're talking, even though we're talking about water, this is true for any hydrogen bonding. We have it in folding proteins, you name it. So it's a really important, that's the reason why I included it. It's kind of weird to have three intramolecular, so metallic, ionic, and covalent, we're creating compounds, but now we have this intermolecular that's between compounds, but I wanted to include it because it's so important. In the last video in this chapter, we're going to look at how hydrogen bonding causes water to behave in such a weird way. And if it wasn't for these weird properties, life wouldn't be possible. So what are our takeaways? We talked about, let me go back up, metallic bonding. The d orbitals of the intertransition metals overlap, and that overlap helps create a bond, but it gives metals the ability to conduct electricity, which is basically moving electrons. Because if we apply moving electrons to this, the electrons can just flow around all of these different nuclei in this sea of electrons. It also is the reason why metals are bendable and can be shaped the way that they are. So our last bonding was hydrogen bonding, which is different because we already have molecules. We've got covalent bonds here. But inside covalently bonded compounds, they don't always play nice. It's kind of like playing tug of war between one of our bulldog linemen in a kindergarten, well, maybe not a kindergartner because that would be completely taken away, maybe a junior high kid. The one that has the greater tendency to gain electrons is always going to win that tug of war. It's going to keep those electrons closer to that nucleus. That's going to result in partial negative charges and partial positive charges that will then attract and form the hydrogen bond. All right, that's all for this video. Thanks for watching and have a good day.